Thank you, Paul. So, a couple interesting news items for you this month. First on the agenda, water on Jupiter. ESA's, the European Space Agency's Herschel Space Observatory has solved a long-standing mystery as to the origin of water in the upper atmosphere of Jupiter, finding conclusive evidence that it was delivered by the dramatic impact of comet Shoemaker-Levy 9 in July 1994. During that spectacular week-long collision, a string of 21 comet fragments pounded into the southern hemisphere of Jupiter, leaving dark scars in the planet's atmosphere that persisted for weeks. Now, our knowledge of water vapor in space basically started around 1995, when the European Space Agency launched its infrared space observatory, which had the sensitivity to get above the Earth's atmosphere, where all the water vapor blocks our view of water vapor outside the atmosphere. So we only discovered that there was water in Jupiter's atmosphere in 1995, a year after the comet had struck. It was widely speculated that the comet was the source, but there wasn't the resolution from that imager to tell. Scientists were able to exclude an internal source of this water in the upper stratosphere of Jupiter because there's a cold trap in the atmosphere that would freeze out any water vapor that would be rising, so it would, that would fall back down. Thus, the water supposedly would have had to come from outside of Jupiter's atmosphere. Another possible source of the water would be a steady rain of small interplanetary dust particles into Jupiter, but in this case, the water would be uniformly distributed across the whole planet and should have filtered down also to lower altitudes. It would be possible that one of Jupiter's icy moons could be delivering water to the giant planet in a giant vapor torus, similar to Herschel has seen from Saturn's moon Enceladus. But this too has been ruled out. None of Jupiter's large moons is in the right place to deliver water solely to the southern hemisphere, as we see in this image here. So Herschel's observations found that there was 2 to 3 times more water in the southern hemisphere of Jupiter than the northern hemisphere, and most of it's concentrated around the sites of where those cometary bolides struck the atmosphere of Jupiter. So quite an interesting observation, and shows how, the dynamic nature of the solar system quite well.
When was this data collected? Is this fairly recent data?
I believe so. It was from the Herschel Hi-Fi heterodyne infrared spectrometer.
Interesting that after all these years, then, that there would still be that kind of degree of localization to the hemisphere when you're talking, approaching a couple of decades now.
Yes, yeah, that is interesting. And you can see, I mean, the resolution isn't great from this spectrometer, but you can definitely see there's a south-north gradient. I'm also interested in why it appears that a lot of it is, very high altitude, like, even in the ionosphere of the planet. You would think if it got up into the magnetic field, it would quickly go around the planet. So interesting. Next. This is a news story regarding tiny grains of silica found in primitive meteorites. Silica, the chemical formula is silicon with 2 oxygen atoms, is the most common constituent of sand or rocks. And so it may not seem odd that small grains of rock have been found in a primitive rock, but it is, in this case, surprising because silica isn't one of the minerals that would condense, the scientists would expect to condense in the conditions that formed the meteorites. In fact, the scientists believe that these silica grains came from ancient stars and pre-exist the solar system. And the reason they think this is because they've measured the isotopic composition of these silica grains, and that is looking at the actual, using a probe, an atomic probe, they can tell whether the oxygen in the silica has a mass of 16 molecular units, or AMU, or 17 or 18. And everything in the solar system has roughly the same isotopic composition. Different stars have different proportions of isotopes amongst their atoms, but the material from our solar system was basically mixed and homogenized in the solar nebula that was formed. So all of the planets have a roughly similar isotopic mix. There are some small differences, but there are much larger differences between different stars. We can actually detect the ratio of isotopes in other stars by looking at the spectral lines that they emit. So we can tell that other stars have different isotopic ratios than our solar system. So all the planets in the sun have pretty much the same composition, and it's called solar, and these grains do not have solar isotopic compositions. 5 silica grains had been previously found before this month, but because their isotopic compositions enriched in oxygen-17, which is 8 protons and 9 neutrons, they were thought to originate from red giant stars as they blow off their outer atmospheres and create planetary nebulae. The silica, because of the chemical composition of these red giant stars, we think that these 5 grains that we had found previously were from some sort of a red giant nebula. The 2 grains that were found in this most recent study are oxygen-18 enriched. And this means that they are likely to have come from a core collapse supernova, which is really cool. A core collapse supernova comes from a very stratified star, and you actually have shells of different atoms inside the star. People have modeled the processes that form these atoms, and they know roughly the composition of these things. And the fact that they found oxygen-18 enriched isotopes suggests that these may have come from a supernova. These grains are too small to see with the naked eye. They find them with microscopes. But because the 2 grains which were found in 2 different meteorites have very similar isotopic compositions, the scientists speculate that they may have come from a single supernova, and perhaps the one whose explosion is thought to have triggered the formation of our own solar system. So quite an interesting discovery. And that's the end. Thank you.